6.2b is trigonometric substitution. It's just the later half of section 6.2, and it's related to our trigonometric integrals, only now we'll start with an integral that will not have a trigonometric function in it, but we'll introduce one because it will simplify the expressions that we're trying to integrate. So if we look at the table given on this page, we'll have three different forms that we'll use or that we'll be able to address with this method. And all of them involve a square root, but the first is the square root of a squared minus x squared. A is some constant, some real number, and x is our variable that we're integrating with respect to. If we have this form, we'll use x equals a sine of theta as a substitution that we'll make. And it seems like that might complicate things more, but it will turn out that thanks to a trigonometric identity, namely the Pythagorean identity, 1 minus sine squared of x, and you can almost see it in this form here, we'll be able to condense that as one term, cosine squared of x. This is easier to see in an example, and we'll see it right away in the first example. But the whole goal of trigonometric substitution is to be able to take a complicated expression under a radical, most often a square root or something involving a square root, and write it as a single term, because if we have the square root of this term squared, the square root will cancel. So that's kind of the main type of problem we'll see for trigonometric substitution. Now the other two forms use the other two Pythagorean identities, or the other versions of these identities. So a squared plus x squared, we set x equal to a tangent theta, and that identity condenses us to a single term. Normally, when we're able to condense things to two terms to a single term, it will simplify our integral and we'll be able to complete the integration. We'll see this in all the examples from this section. And finally, we have x squared minus a squared, which is a variation of the identity above. But only in this case, we use x equals a secant theta, as we see here. So the trick to trig substitution is to recognize your form and use the correct substitution. Usually from there, it's just a matter of simple trigonometry and calculus to work your way through the integral. So we'll start simply. We're asked to evaluate this integral, x cubed times the square root of 1 minus x squared with respect to x. So after some practice in chapter 6, hopefully students will start to see what tool they need to use. And I guess the thing I could give a hint for is if you have a troublesome radical, troublesome square root, then it's probably a good idea to use trig substitution. That might get you out of it, especially if you see something plus or minus something squared or vice versa. So what we recognize now is we have a squared minus x squared as our form. We have 1 minus x squared, or 1 squared minus x squared. So a squared is 1, as we see here. So a is then equal to 1. We'll take the square root of that. We'll just take the positive version to make things easier, right? Remember that we use the substitution x equals a sine theta, and that's exactly, this is a showing up right here, sine theta. So a is 1, so it's 1 sine theta. So really x is just sine theta in our substitution. Now let's check to see what happens. And this isn't the way you have to do it, but it's nice to take this expression and rewrite it here after you make this substitution and see that it does simplify things. And in fact, we see that right now. 1 minus x squared is equal to 1 minus sine squared theta, thanks to our substitution of x equals sine theta. Well, 1 minus sine squared theta is cosine squared theta. That's the Pythagorean identity solved for cosine squared theta. And that is going to be useful. We have 1 minus x squared under this radical, and that was giving us a somewhat troublesome integral. Now we can substitute 1 minus x squared for cosine squared theta underneath this radical, and the square root of cosine squared will be cosine. But first we have to take care of one more detail. We're changing the variable from x's to a function of theta. Right, so we need to change dx to d theta. Well, that's pretty straightforward. The substitution we made to start with is x equals a trig function of theta. So all we have to do is find dx, or take the derivative with respect to theta of both sides. We have dx d theta and solve dx to get cosine theta d theta. Now remember, we took the derivative of sine theta, and that gave us this cosine theta. And then we solve for dx to get cosine theta d theta on the right-hand side. And then lastly, this is an extra step, but it's just nice to see it. X cubed in our integral will become sine cubed theta. We're very happy about the fact that this condensed to a single term. That's what smiley face is. Looks like it's going to work out in our favor. So we'll continue in the blue text. The stuff in black we'll see at the very end to clean up the problem, to come out of our substitution. But for now, we've got 1 minus x squared is cosine squared theta. That is underneath the radical. X cubed we saw is sine cubed theta. And then dx is cosine theta d theta. So all of our parts are replaced. Sure, it does look more complicated, but the most important thing to happen is the two terms underneath the square root have become a single term. We have the square root of cosine squared theta. That term is going to become just cosine theta times the other cosine theta. So we have cosine squared theta and the line below that. And that all, of course, is times sine cubed theta, d theta. And really the utility of this method is that it reduces us to a form of 6.2 part A, the first part of this section. So we know what to do from here. If we've been practicing the first half of the problems from 6.2, we need to peel off a copy of sine because that's the odd exponent. And that sits out here as sine theta d theta. And now we look and say, well, if this is our u substitution, if u is going to be cosine theta, then sine theta d theta is our du. So we need to put everything in terms of cosine now. So in other words, this sine squared theta needs to become something in terms of cosine. Well, the Pythagorean identity does exactly that for us. Sine squared theta is 1 minus cosine squared theta. And that's what happens between these two steps. Of course, cosine squared theta is still cosine squared theta here. And in between, we've made our u substitution. U is cosine theta. Du is negative sine theta d theta. And we have du sits right here. This is all of du sine theta d theta. So just a negative du will replace that term once we begin our u substitution. This is sort of a half-written u substitution. It's not a very well-written step right here because it's mixing variables, but it's okay. We're on our way. We're not going to integrate without fixing that. And of course, 1 minus cosine squared theta is 1 minus u squared. And then we've got u squared times that du. So this is just a polynomial integrand. We can integrate this, but first we should probably distribute that factor of u squared across the binomial. We have u squared minus u to the fourth du, and the power rule leaves us with 1/3 u cubed plus 1/5 or minus 1/5 u to the fifth, and this minus sign was times each of these to change their signs. So the integral's gone away. We've added plus c, and we've got our antiderivative or indefinite integral in terms of u. Well, we know that u is cosine theta. So now we can back out of this portion. This is negative 1/3 cosine cubed theta. Similarly for 1/5 cosine to the fifth. And lastly, the last trick and the last difficult part of this is to remember our integral was in terms of x. If we look at the top, we see that. This was an integral with respect to x of a function in x. We have something in theta. We're not quite done yet. So what we need to do is we need to figure out what cosine of theta is with respect to x. And the only thing we really have to go on is this information up here. We know that x is 1 times sine of theta. So let's use that fact in the definition of sine of theta. Sine of theta is opposite over hypotenuse. So x over 1, x over this 1 is equal to sine of theta. We might write it that way just to see it. And that's what happens over here in the black text. We've got x over 1 equals sine theta. That's opposite over hypotenuse, x over 1. And here we have opposite. Here's our hypotenuse of our angle theta here in this corner. And our last side, using a squared plus b squared equals c squared, where this is b and this is a. This is c, so c squared minus a squared, square root of that, leaves us with square root of 1 squared minus x squared. Now something you'll see a lot, this was a term that was in our integral, and this shows up from our triangle to back out of our substitution. So that connection is always nice to see. Don't always rely on it. You should be able to use the triangle to get out of this because sometimes things will be a little messier, but you'll tend to see that same term show up. So now looking at the triangle, we can find what cosine of theta is. Cosine of theta in this position is the adjacent over the hypotenuse. So there it is. It's going to be that square root of 1 minus x squared over 1, which is just the square root of 1 minus x squared. And that's down below. So we finish off with negative 1/3. Here's our expression for cosine theta cubed. Similarly, cosine theta to the 5th, and everything else is held in place. No need to simplify any further than that. That's fine. We could write to the power of 3 halves and the power of 5 halves if we want to get rid of the radical, but that's just details. Okay, so to sort of recap the steps, and then we'll have a second video to do some more examples. To recap the steps in this most basic problem, you recognize the form, you recognize what a squared is, and then from there you can choose what your substitution needs to be. You're always going to let x equal a times some trig function, a being this number, and the trig function being determined by whether or not it's a squared minus x squared, or x squared minus a squared, or x squared plus a squared. A check for that, and something to help you clean up the integral as you progress, is to write down the troublesome term under the radical and see what it comes out to, and see if that's going to simplify in the square root, and it will. In this case, it did. And if it does, then you're good to go. And then you can find dx d theta, solve for dx. So you have cosine theta d theta, and you make all of your substitutions from there. After you get through all of that, you might need some techniques here, right? Of course, we needed a u substitution. That might come up, so be ready for that. Be ready to handle these trigonometric integrals that we've had in 6.2a. Once you are able to evaluate all of that, you're back in theta. Just don't forget, you need to get back into terms of x, and this requires some trigonometry. And it might be a little daunting. You might not have done this much trigonometry between now and your last trig class, but this really is just right angle trigonometry that's happening here. So really get in there, try to get your hands on it and see what you're doing with it, and it won't be as bad as it looks. You draw this right triangle, you say, this is theta. I know that sine of theta is x over 1, and that's always coming from your initial substitution. And you're able to say from there that if I have an arbitrary triangle that I just drew, a right triangle, and I put theta in the corner, and I look and say it's opposite x over hypotenuse 1, then I can fill in this with the Pythagorean theorem, and now I can say cosine theta is the adjacent over hypotenuse, and from there it's pretty easy. So that's it for 6.2a, the first, or 6.2b, the first video. I'll make another one with 3 more examples, and keep working from there.